This week we're going to learn about data visualization. When I think about visualizing data, I think of the proverb that a picture is worth 1,000 words. And the idea being that an image can convey a thought more quickly and effectively than text. So data, in high-dimensional data, just like other data, visualization is an important first step to data exploration and an essential part of your data analysis. So any analysis should begin with assessing the quality of the data. Here, the goal would be to identify and remove failed samples or outliers from your data set. So here on the left, I have density plots. So in this data set, we have 24 different samples, and this is a stacked density plots of these 24 samples. And the values range from a little below 4 to about 16, and that's on that log intensity scale, with most values occurring down in the 5 to 6 range. So those are that most of the genes are very lowly expressed or not expressed in that tissue sample. So by the design of the array, it kind of causes that bump to occur in that position. So we'd look for a failed array that might have a bimodal distribution or just looks strange compared to the others. But like I say, these data were clean, so we don't see that in this figure. Now for outliers, looking at plots individually for each data set for each array is unlikely to find an outlier, because an outlier is defined by being very different from all the other observations. So really we want to do something more like compute the distance from each object to all the other objects and see if it's far away in that sense. So on the right is a heat map showing the pairwise between sample dissimilarities. So it's capturing whether the samples are similar or here dissimilar. Larger values are being dissimilar to each other. And this would give us an image about an outlier. So if one of the points has the high red value across the entire row, one of the samples, we'd know it's very dissimilar to every other sample in the data set, and that would flag it as being an outlier. So how do we define these distance or dissimilarity measures? So let me go and give you the 4 properties of a distance metric. So the first property is that if you take the distance between points A and B, it is greater than or equal to 0. So distances are not negative, non-negative. Also, the distance from A to B is the same as the distance from B to A. So there's this symmetric property of it. The third property is that the distance from A to itself is 0. And then the fourth property is the triangular inequality, that a distance between A and B is less than or equal to the distance from A to a different point I, and from the sum of that with the distance from I to B. So here are 2 examples of common distances that we use in analysis. One is Euclidean distance, and that's taking the pairwise distance differences between 2 samples for each feature, squaring that difference and summing it over all the features and taking the square root. Manhattan distance is the other, which is just taking the absolute value of the differences and summing them. I'm having a hard time talking. Summing those over all features. So with Manhattan distance, that's also sometimes called city block because it's just adding up those absolute value differences. Okay, so we can also measure dissimilarities between 2 observations, and I'm going to give you here I'm going to start with an example of what a dissimilarity is, and then we'll go to the properties and see how dissimilarity is different than a distance. So an example of a dissimilarity is 1 minus the correlation between 2 points A and B. So in statistics, when we have quantitative data and we're looking at how the relationship between them. So pairwise, one of the ways we measure similarity is through the correlation. So that would measure the linear relationship between 2 variables. So we have pairwise correlation as a statistical quantity measuring similarity, and dissimilarity would then we could compute from that using 1 minus our similarity to get. So now If correlations from -1 to 1, our dissimilarity would go from, I guess if it's -1, they're very dissimilar. 1 minus 1, 1 minus minus 1 is 2. So those become a 2 is very highly dissimilar. And if they're perfectly correlated, then the correlation is 1. 1 minus 1 is 0. So that would be a range from 0 to 2, with 2 being most dissimilar and 0 being linearly correlated. We could also, if we don't, we could also use absolute correlation. That would fit the properties of dissimilarity as well. So let me talk about what those properties are. There are 3 of them. The first one is just like the distance property, that the dissimilarity between 2 objects has to be greater than or equal to 0. We also have the symmetry property, that the dissimilarity between A and B is the same as between B and A. And we have the dissimilarity of an object to itself being 0. What we do not have, there are only 3 properties, we do not have that triangular inequality. So if you have something that meets the first 3 properties and not that triangular inequality, we call it a dissimilarity and not a distance. So there's a difference between the dissimilarity and the distances. So going back to our calculation, we can take our high-dimensional data set with p features and on n samples and apply a pairwise dissimilarity between our n samples and come up with, and here I'm just drawing this as a triangular matrix because we know the diagonal values are the dissimilarity from an object to itself, which is always 0, and we know there's this symmetry property. So you'd be able to flip this triangle, so the upper triangle is the symmetric values of the lower triangle. So these are the represent what would be the unique measurements between all pairs of observations in the data set. And that's what we would plot in the heat map. So here's the heat map one more time. Now for outliers, the choice of dissimilarity that I've used here is to look at, for all pairs of samples, compute the absolute distance for all measurements across the genes. So for feature F, take the distance between sample A, sample B, do that for all genes, take the absolute value and get the median of that. So if that median value, so if half the genes on the array are very different on an absolute value scale, then that sample is probably an outlier or different. You've got 2 very dissimilar arrays. So visualizing data should not be limited to data cleaning. We're also very interested in whether we can visualize biological patterns in the data. So here are 2 approaches that would allow us to visualize high-dimensional data. The goal of the dimension reduction techniques is to reduce the dimensions to a very few and still maintain the structure as much as possible in the data. So in the next video, we're going to watch, I'll introduce the 3 methods listed here. And next week, we'll learn about cluster analysis methods.